Yesterday we started by discussing three-dimensional supersymmetric field theories on a round sphere S3. I outlined the procedure of localizing these theories. So we start with using gauge theory. On S3, and we end up with a matrix model. So the procedure was quite general. It was applicable to many theories with at least n equal 2 supersymmetry, though the details I gave required a little bit more. And today we're going to focus on ABJM theory. So ABJM theory is the gauge theory dual to the theory living on, it's the gauge theory description of the M2 branes of M theory. Actually, for a lot of what I'm saying, we can ignore the M, the ABJ theory, which most of what I say is applicable to it as well. So this theory fits into this more general class in the following way. It's a UN1 cross U and 2 a gauge theory. So sometimes I will assume N1 is equal to U2, but not necessarily. That was the case originally considered in the paper with Maldacena. In the paper without Maldacena, they considered the generalization. And it's a conformal theory, so we're not including the Young-Mills term, but we have Chern-Simons terms at level k and minus k for the two groups. So this is the Chern-Simons level. And in addition to that, there are four, so there are gauge fields for this, there are gauge fields for that. Since if we want to work in a superspace formalism, or have full explicit supersymmetry, we include the sigma and lambda fields in the vector multiplet. And then there are four chiral fields units in my fundamental representation. So anybody who is familiar with river graphs, you have 1, 2, this is the quiver. If you don't know what that means, it just means what I said. So this theory, it stands as n equals 3 supersymmetry. To enhance supersymmetry, so if we choose with a particular superpotential, Suzy is enhanced from n equals 6. Now, anybody here remembers the role of the superpotential in the discussion yesterday? Perfect. answer. There was no role for the superpotential in the discussion yesterday. So, the fact that it's enhanced from n equals 3 to n equals 6 doesn't matter, and if we consider ABJM without the superpotential, which is not ABJM anymore, it's just this quiver without the superpotential, we'll get the same matrix model as with it. So it's one of these weird things about localization. It doesn't see everything about the theory. I mentioned it already yesterday. If there was a Young-Mills term in the action, it wouldn't see it. If there is a superpotential term, it doesn't see it, because the superpotential is Q exact. It's a superpotential terms can be written as a delta of something, as a supersymmetry variation of something, so they don't affect the localization calculation. So if you want to really describe ABJM, you need this superpotential. When you do localization, it doesn't matter at all. So we can read from this diagram or from the description above what is the matrix model for ABJM. The partition function for ABJM on S3 is equal to 1 over. So I'm putting here some factors to get things correct. Some normalizations. It's not crucial. So we have product I equals 1 to n1 sigma I. Product I equals 1 to n2 and d sigma prime I. We have transience terms, which we said in the matrix model become Gaussian terms. Pi I k sum I equals 1 to n1 sigma I squared minus sum I equals 1 to n2 sigma prime squared. And then we have, so this came from the classical, from the transience action, classical contribution. And then there was the one loop contribution, the fluctuations, where from the vector multiplets, we got product I less than k less or equal to n1. Pi sigma I minus exactly that, and for the other group, then there is the contribution of the matter fields, which I didn't have time to go into calculation in detail yesterday, but I told you what the answer would be, and that is product I equals 1 to n1, k equals 1 to n2, 2 cosh pi Okay, so this is what we calculated essentially yesterday. We did it much more generally, but then it's very easy to apply it to this theory. This line, this node gives us this thing, this node gives us that thing, and the exponents, and these lines in between give us the denominator. So this is the matrix model. As I said, it doesn't depend on the superpotential. There's actually there are actually supersymmetric deformations. I had this question yesterday, so I'll tell everybody. There are actually supersymmetric deformations of the sphere, so you can consider certain manifolds that are not around S3 and will have the same. They are going to have the same. You can still have supersymmetry on them by turning on some background fluxes, and you can still localize on them. And there's actually a very large family of metrics like that, and but for all of them, as far as I know, they can only introduce a single extra parameter. It's called B, which appears. These cinches, this sinh square becomes sinh of B times this, and sinh of 1 over B times this. And there is a more complicated deformation of the denominator usually. So there is a deformation of this if you take a squashed sphere. But again, there are many, many different ways of squashing the sphere, and at most you get one new parameter, continuous parameter, B. So this is one case where certain allowed supersymmetric change will change the matrix model. But again, like introducing the superpotential or these many different deformations, not all of them will change the answer. Anyhow, we will concentrate on this case without B or with B equal 1. So this is the ABJ matrix model on the round S3. So I'm not going to localize anymore for the rest of my talks. I will be using good old matrix model techniques to solve this matrix model. So these were developed many years ago, but there are still improvements these days in tools to solve matrix models. And the first thing that we do is let me write everything in the exponent. So this is equal to 1 over n. Right, so this was written for ABJ. So whenever I'm lazy, I will set n1 equals to 1. For now, I have energy. And I squared minus squared plus 2 I less than j log of sinh I sigma j plus 2 sigma I j log sigma sinh I sigma j prime minus 2 sigma I j log cosh I yes sigma j minus So what is important about this expression is we want to solve it in the large n limit. So we need to check how the different terms scale as we go, as we take n to be very large. So you see that here I have a sum over I and j, each of them going up to n. I'm assuming, even if n1 is not equal to n2, that they are both comparable. So this will behave like n squared. This term also behaves like n squared, or n squared over 2, which doesn't really matter to us. And here I have just a single sum. So this goes like n. So if we take the large n limit, we would find that these terms dominate and the Gaussian completely goes away, so we just have some matrix, some measure, and all the potential disappears, except if we assume that k also behaves like n. So this is the 't Hooft limit, which is the correct large n limit, where k over n, we call it lambda, and we keep it fixed in the large n limit. And then all the terms here will be the same. I mean, note, this is of order sigma squared. This is of order log sinh of sigma, so it's proportional to sigma. So sigma and sigma squared and so on, they will not need to become very large in this limit. They will remain of order 1. So now in this limit, we want to solve it somewhat classically. So we view this, everything that appears in the exponent, as an action for the eigenvalues. And we're going to write the equations of motion. So x, we can view it as s sigma I prime. And we can write the equations of motion, partial s, partial sigma I. So we're going to look at the saddle point of it. So we're going to get a term proportional to sigma I from here. So I get 2 pi I k sigma I plus 2 some j different from I. I differentiate this log of sinh, I get cos cotangent hyperbolic, the pi from here of a pi sigma I minus sigma j. This term will not contribute, and here I have minus 2 pi sum over j, tanh sigma I minus sigma j. And to be consistent with my notations, please forgive me. I will change this to a plus, and this to a plus, and this to a plus. This is no change at all, because I'm just changing sigma prime to minus sigma prime in the integration. That will give you a minus 1 to the n power of n2. But let's forget that. And this will have 2 minuses. That is squared, so that doesn't change. So you can do it either way, but my notes have a plus there, so I will make a mistake if I don't change it. So we demand that this is equal to 0, and we take the derivative with respect to sigma I prime, and this is equal to minus 2 pi I k sigma I prime plus 2 pi some j difference from I cos I sigma I prime minus sigma j prime minus 2 pi sigma j times I sigma I prime plus sigma j. And we demand that this is 0 too. So now we need to solve these equations for 2n eigenvalues, or n1 plus n2 eigenvalues. So we have a very large matrix equation for these eigenvalues. So that's still a hard problem, but the way we solve it is by assuming that these eigenvalues condense into two cuts. So we have say the eigenvalues sigma sitting here. So these are the sigma i's and sigma I primes sitting here. And then in the large n limit, we can assume that this goes over to contiguous sets. So that's the same way that you treat data roots in thermodynamic limit. So we define the, now I drew it here in the same plane. You would normally have to deal separately with a eigenvalue density of sigma and sigma prime. These are two independent cuts, but actually we will see that we can put them both in the same plane and treat them with the same function. The same function would have a support here and here, or a cut here and here. So let us define the eigenvalue distribution. Rho of lambda, which is equal to 1 over n, sum over I, delta of lambda minus sigma I, and take quantum average z, and rho prime of lambda equal to 1 over n, sigma I, delta lambda minus sigma I prime. And now we can write these equations in terms of the eigenvalue densities, but it's even easier if we define the resolvent, omega of z to be equal to 1 over n, 1 over some over z minus sigma I. So this we can use this eigenvalue density, we can also write it as integral the sigma rho of lambda sigma minus lambda, that is the resolvent. Well, z minus lambda. Sorry? Yes. So, we can see what are the terms that will appear here, and what we would expect is then that the resolvents have the form omega 1 of z is equal to I over k sum over I cos I z minus sigma I. So that is different. So normally it is, you define it like this, but it will be useful in this case to take these expressions. So you really want to take the resolvent to be whatever you have here on the right hand side, and omega 2 of z is equal to I over k sigma I equals 1 to 2 cos I z minus sigma I. So this is what we define as our resolvent, and what we then try to do is write the equations of motion in terms of this resolvent. So this we can write because we have an equation which is roughly of the form, how should I say it? So this equation is 2 pi I 2 pi I k sigma. Here I have the sum where j is different from I over this, which is the first omega. So this is something like I over k principal value of the integral of omega 1 of z. And then plus I minus and there should be the 2 pi. If I shift by I over 2, this cough will become the tanh, so I get this expression. So here I have the equation for sigma, and you get a similar equation on the other cut. We have small numerical mistakes there. But then we can interpret this as an equation for the jump in omega. We can take here the principal value of omega should be equal to sigma integral of that. So you get an equation that tells you that omega at z plus I epsilon minus omega at z minus I epsilon is equal to minus 1 over 2 pi I rho of z. The eigenvalue density is the difference between the two resolvents that we take. So we can define omega equals omega 1 plus minus omega of z is equal to omega 1 of z minus omega 2 z plus I. So this is true for the total omega, and now I have, so you can change this integral above to a, well, not quite treat it that way because we need to integrate over the two different cuts. But omega will now have two different cuts, one corresponding to omega 1 and one corresponding to omega 2. And the other equation is that omega at z plus I epsilon plus omega at z minus I epsilon. That is essentially what you will have here. It's what is left of this, that is this principal value prescription. And that should be equal to 2z. So we have here an equation that we need to solve for the discontinuities of this resolvent omega. And this was actually solved by Marino and collaborators, and by, actually in this example, by in this way, by Harmaki and I forgot, Yasmo.
How do I know where this jumper is placed? The sound says that the omega 1 is in the ordinary matrix model.
Sorry? We don't know where it is.
How so? We don't know the value of the jumper. We don't know where.
We will solve it self-consistently. We will find where the cuts are. We don't know now where the cuts are. So we just assume, we assume here that there are two cuts. Which is not necessarily true, but we assume that the eigenvalues all will stay close to each other. There usually is a solution like that, and this would be the dominant solution. And then we write down what would be the equations, which is what I wrote here, and then we find where these cuts are. So these equations are enough to determine where the cuts are. This doesn't come in as input. So there is an n should be okay. So let me consider the function is equal to e to the I lambda 1 minus lambda 2 e to the 2 pi omega naught plus z squared e to the minus 2 pi omega naught, where capital Z is equal to e to the 2 pi little z. So I define the function in terms of this omega, and now the claim is that assuming this property, f is a single valued function. So we can check that. So sorry? Omega is it's actually going to be the planar solution to this, but I'm going to ignore the distinction between the full resolvent and planar resolvent. So let us let us evaluate it at above the cut. So f plus is equal to e to the I lambda 1 minus lambda 2. Lambda here are the two at Hooft couplings. So lambda 1 is equal to k. Sorry, oh, this was bad. And over k is an at Hooft coupling. 1 k is equal to 2. So I have e to the 2 pi omega plus, which is this thing, plus e to the 2 pi, the 4 pi z, e to the 2 pi minus 2 pi omega plus. And now I use this equation to write this as e to the I lambda 1 minus lambda 2. E to the 2 pi omega plus is equal to e to the 4 pi z minus 2 pi omega minus. Replaced it here. And now I have plus e to the 4 pi z minus 2 pi times 2z minus omega minus. And now you see that this is solved. So this term cancels this term. I get plus 2 pi omega minus, and here I have 2 pi omega plus, and here I have e to the 4 pi z minus 2 pi omega minus, and here I have 4 pi z minus 2 pi omega plus. So this function doesn't change when I go from omega plus to omega minus. So this is a single valued function. Actually, you need to check it along both cuts. So you need to check it along the cut for the sigma and the cut for the sigma prime. But this indeed works. So we have the solution, so we have a single valued function, f of z, and now we should look at what are the asymptotics of it. So f of 0, this will be equal to e to the I lambda 1 minus lambda 2 plus 2 pi omega at little z infinity. So little z, so omega, we defined it in terms of the different, omega is omega 1 minus omega 2. We need to take little z going to minus infinity. The cost there will become a minus 1. Here in omega we have omega 2 shifted, so we will have a tanh that goes to 1. So we will have the difference. Each of those eigenvalues will give me 1. Each of these eigenvalues will give me a minus 1, and I'm going to get a 1 over k. So this is equal to minus I over k and 1 minus n2, which is exactly lambda 1 minus lambda 2. So this is equal to 1. F at capital Z goes to infinity. It's equal to it's equal to Z squared. Let me write it in terms of little z. So the term that will dominate in that limit will be the second one. So I have e to the I lambda 1 minus lambda 2. Now let me write capital Z squared, and then e to the minus 2 pi omega at little z goes to infinity. And again, now you have the different limit where this goes to 1 and this goes to minus 1. But you have here a minus sign, so again this term cancels this term. So this is equal to z squared. So we have this function f, which is regular, is 1 at the origin, is z squared at infinity, so it's a quadratic form. So we can write f of z is equal to 1 plus the linear term, which I'll take it to be I kappa z. It will turn out that kappa at the end is real, otherwise I wouldn't call it like this. But at this moment I don't know whether kappa is real or not. Plus z squared. So this is the solution, and it satisfies this equation. It's defined like this in terms of omega naught. So omega naught, omega, the planar resolvent, I can solve this equation and write omega in terms of f. Two pi omega is equal to log of e to the minus I lambda 1 minus lambda 2 over 2 f of z minus square root square of z minus 4 e to the 2 lambda 1 minus lambda 2. So this is the solution, but as you said, we still don't know where the cuts are. The cuts are now given by so they're going to be, f is quadratic, so f squared is a quartic. So we're going to have 4 branch points for this square root. So there are going to be 4 points. So we're going to have 2 cuts as we expect. That's good. and they're all going to be given by lambda 1 and lambda 2 and by kappa, which are the things that are not written down. We don't know yet what they are. So we're going to need to solve for them. So normally if you have a quartic polynomial, you're going to have a bunch of coefficients. You have a choice of 4 roots. In our case, things are simplified. We actually have only 2 parameters. We have kappa and this lambda 1 minus lambda 2, which we could actually take if we would look at the case where n1 is equal to n2, this would be 0. So we're just going to have this one parameter. But actually, you can see that there are some symmetries that would reduce the number of free parameters. So you would expect in the sigma plane, in the little z plane, you're going to expect a symmetry sigma going to minus sigma. So your cuts in terms of sigma are going to be symmetric. Then, because capital Z is the exponent of it, you would expect Z going to 1 over Z. So this is why I take the ansatz that f squared minus 4 e to the 2I lambda 1 minus lambda 2 z squared is equal to z minus a, z minus 1 over a, z plus b, z minus plus 1 over b. So in this picture, this is a, this is 1 over a. Minus 1 over b. Now, so this is not, as I said, this is not the most general ansatz for a quartic polynomial, but I will actually be able to solve it. So this tells me that what I did was correct. So here you see I have I have z squared minus I, plus or minus, plus I kappa z plus 1 squared minus 4 equal to 2I lambda 1 minus lambda 2. So the highest term is fixed, the lowest term is fixed. The cubic term and the linear term are related, and then only the quadratic term, which will include this and will include this and this, will see this lambda behavior, and this would actually satisfy this. So you can see that the solution to this equation is that I kappa will be equal to a half a plus 1 over a minus b minus 1 over b. So this you get from the cubic term. So if I look at the cubic term here, I get 2I kappa z squared, so 2 I kappa z cubed. And here I get a minus a minus 1 over a plus b plus ib. So I think I did it with the wrong sign. And then it works. And then, so we fix that. You can also check that the linear term is satisfied with the same condition. And then we just have the quadratic term, which will give us that a b to the I lambda 1 minus lambda 2 is equal to 1/4 of a plus 1 over a plus b plus 1 over b. And in particular, for a lambda 1 equals lambda 2, that's the ABJM case, we find that a plus 1 over a is equal to 2 plus I kappa, and b plus 1 over b is equal to 2 minus I kappa. So this is essentially the solution. We found what omega is, and we have this free parameter kappa, or the endpoints a and b, kappa and lambda 1 and lambda 2. So you see, if I write it in this way, I actually, you know everything in terms of kappa, but you don't know how kappa is related to their code coupling. So this is something we still have to solve. How is kappa related to lambda 1 and lambda 2? We have the difference of lambda 1 minus lambda 2 appearing in there if it's different from 0, but we don't know what kappa is. So we have this matrix model. We have, so this is the capital Z plane. Actually, that picture should be in the capital Z, where we have here 1, minus 1, and we have the two cuts opened around plus and minus 1 in the imaginary direction. And we have a 1 over a minus 1 over b, which are somehow close to 1. In some limit when we have a small number of cuts. And as I said, we don't know, we have it, everything. We can calculate in principle everything in terms of A and B, but what can we calculate? So, for example, we have this omega, which is defined as a function of, actually it was originally defined as a function of this sigma, or this little z, which is the log of capital Z, but we can define it in terms of capital Z, and we can integrate it around here. I'll call this curve C1, and I will call this curve C2. So what is the integral of omega z bz around C1? i's that I put in there. What does this calculate? So,
It's the number of
exactly. Exactly. So it calculates the number of eigenvalues in the cut. So remember that this cut is made out of condensation. What we did is started with omega is roughly the sum over the poles. If we calculate the integral, the contour integral around this, we will pick up a 2 pi I from each pole. We're going to essentially get the same from doing the integral over the resolvent. So with this normalization, this will give me n1 over k, which is lambda 1 minus a half integral c2 is equal to n2 over k, which is lambda 2. So now I have all the information. I have the relation, here an algebraic relation between A, B, kappa, lambda 1 and lambda 2. And here I have another integral relation between A, B, and kappa. A, B that appear in omega, or kappa, and lambda 1 and lambda 2. So if I can evaluate this integral explicitly, I need to integrate this log of a square root of a quartic. Then I can calculate then I can solve everything completely explicitly. So let me do that after the break. In the meantime, you can think about how to integrate that function. Any questions? Yes.
The question, what is the exact shape of this path? Because in the ordinary matrix model, we know that they are placed very ellipses because the values are real, but here we cannot choose one of the shapes, possible shapes.
What do you mean by shape?
Is a plan or something curvy?
Well, in the way we solve it here, it doesn't matter how, right? Because you choose, now you use an analytic function. So at this level of the approximation, it doesn't matter. As long as it's continuous, it doesn't matter what is the shape of the cut.
Yes, but maybe in the physical problem we can ask this question or not. For the solution of some equation, the answer is that there are infinite solutions corresponding to all possible shapes or not.
Yes, so at the planar approximation, it doesn't matter because we can solve it by this analytic function, and then the shape of the cut doesn't matter. If you go to a higher genus, I think this will essentially give you more detailed information of the eigenvalue distribution.
But if you ask about quotation of, say, it means that we have many possible several points given by
Yes,
distributions of sigma.
that's right.
So we don't need to integrate over all possible distributions.
No, I don't think so. I think so. This is just an artifact of this approximation that you do not determine the specific eigenvalue distribution. It's not important for the solution, and it's not for the solution at this level. So all we need at this level is where are the branch points, and that gives you all the information for the planar theory. see that it's self-consistent to take. So this, in terms of this little z or sigma, that the cuts are parallel to the red line. So here they are. So here they are close to. Yeah, I don't remember. They're at least they're a. So there is another way to solve this matrix model, which was done in one of the references I gave yesterday by Klebanov and others. And there, the eigenvalue distribution is straight, is in straight lines, and it's linear. So it's a much cruder approximation. It doesn't give all the planar result. It just gives the leading order at large lambda and large, not large and exact in lambda, like this calculation gives. But in that approximation, the eigenvalue distribution are piecewise linear along the real line. So you can start with that and then refine the approximation if you want to know what is the exact eigenvalue distribution. Any other questions? Yes?
So we found 4 branch points.
Yes.
How do we know that the cuts are connected as they are and not, for example, across? So I understand that the exact form of the cuts is not determined as this, but the 7-point equation, they give a particular form of the cut, particular position, don't they?
That's right. So actually, it is something I'm confused about because I drew these and I remember having Mathematica codes where actually they were opposite. The curves, the C curve was going from here to here, but this was a long time ago that I looked at that picture, so I'm not completely sure. Can I think about that and give you the answer after the break? You don't have the answer.
No.
Anything else for me to think about? So you're supposed to integrate this.